The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Last question, I will continue. So again, I think what you're saying is a trajectory that we start. So it's a very steep dive. We start from a very basic thinking, and then really trying to understand the materials, what determines the material properties. And this lecture, what I'm hoping after I close up with you, listen topic in terms of thermal conductivity, what I'm hoping is bring you to real from here. What people are thinking in making materials better. So, but let me start with just a very brief review of last lecture. We show one is simple. Remember, my picture is always simplest picture is always from left to right and right to left, and the difference gives you the flux. So from there, we show the general relation. The current flux, like this. The current flux is related to electrostatic potential. So that's the charge driving force for charge flow. And then we will have a temperature gradient. It's comparable to the temperature gradient. So now you see the electricity to heat coupling. And then this one shows the heat current. So really now electron is carrying the heat as a heat current. This is the electric current, heat current. It's again coupled in this case not just to temperature gradient, but also to the electro potential gradient. And this is a very general ensemble relation. If I have written this gradient in terms of generalized force, those coefficients, cross coefficients are equal. This is what the sort of answer on the lower price mentioned before. And then I gave some, if we use some of the concepts we learned before, for example, density of states, and we have expression for this coefficient. L11 is the electric conductivity, and those other coefficients from those other coefficients, we can calculate Seebeck coefficient and the Tauke coefficients. Let me just make one remark that those expressions are not the most general. You can have different transport regimes. This is the regime that most people do, the Boltzmann transport regime. So those expressions you can, rather than my time-weighted derivation, you can actually start from Boltzmann equation to derive those coefficients. And I showed examples. One thing that I want to emphasize is that the properties depend on temperature. So different temperature, you can see the property are changing. For electric conductivity, if you follow the simple Boltzmann statistics, you actually get the electric conductivity in semiconductor. We know typical microelectronics type of doping, electric conductivity increase with temperature. But for thermoelectric material, so this is not right. For thermoelectric material, you can say the thermal conductivity, electric conductivity decrease with temperature. And that's because we're doping very heavily. Metal is like this. In metal, the electric conductivity decreases because when you get a hot, there are not more photon. The atoms are vibrating more violently, and that's scatter electron. And that's why the electric conductivity will decrease. And the Seebeck is typically have a peak. And if you just talk simply one band transport, so one band means if I have a conduction band, And if electron only going to one conduction band, then the theory says it should increase with temperature. Because as the temperature increases, the separation of the chemical potential from the bottom, so you drive chemical potential to the center of the band. But in almost all materials, the behavior is it will peak at some temperature and start to decrease. And the reason is as the temperature increases, you excite the intrinsically, you lift the thermal energy, lift electron from the valence band, create a hole behind, drive electron to the conduction band. So in this case now you have both electron and hole. So when you flow current, electron carry energy in one direction, hole carry energy in the opposite direction. So they cancel each other. In this case, you actually could get a higher electric conductivity, but the C-like start to cancel each other. So this is when you look at experimental data. It turns out that many times we do that and say we cannot calculate exactly. So we look at experiments and this is what happened. This is why it died, and this is where how you can move this to higher temperature. If you have more electron, you dope it more heavily, you will go to higher temperature. And if you have larger backgap, it's more difficult to generate the thermal electron hole pairs, and then you can move this to higher. So that's how you look at the different temperature range and these different materials. So that's where we were in the last lecture, and those were mainly discussion on electrons. And we also talked about the photon, the concept of lattice vibration, and we gave a very simple expression before on the photon thermal conductivity. And again, my picture is left to right, right to left, right? So when I want to find out the heat flux going through any plant, I see how much heat is going from one side to the other without scattering. So this is with one relaxation time, and how much from left to right within one relaxation time. The difference can be the heat flux. And what I want to do is a little bit more better counting. Meaning, before I was just saying this is Lambert density, N, right, per unit volume. Now I'm going to do moles. So I'm going to sum up. So this is it's the same as what I drew here, but here is more rigorous. So this is the energy of one photon, lattice vibration, quanta of lattice vibration. So one photon, and then this is per quantum mechanical modes. That's the Bose-Einstein distribution, right? Per mole, per state, quantum state, how many photons you have, right? And this is the velocity. So this is really telling me per quantum mechanical modes how many photons is moving to the forward positive x direction. The one half gives me half random motion. So the idea is the same, but now I'm trying to do a better job, better counting job. And here, what we have, this is, remember in the second lecture, I was doing black body counting, black body radiation, right? So this is counting all the quantum mechanical allowed modes, kx, wave vectors, right? It's a photon wave, kx, ky, kz. So I'm summing up all those modes, and that's from left to right, minus from right to left, give me the left flux. So that's what we showed before in simpler form, but if I do this, okay, and I will get the integral, no longer just a simple 1/3 CV gamma, that's what we had before, and now it's integration of all the frequency, each frequency. Remember photon, so the acoustic wave, for example, low frequency acoustic wave, that's what you hear, and they have the different mean free path, different group velocity, than higher frequency ones. So this can all change as a function of frequency. So what we're writing now is a more rigorous form for the thermal conductivity carried heat conduction by the lattice vibration photons. Okay, so this is a typical, you take a bulk material, right? And people have measured the thermal conductivity, and this is a typical curve of thermal conductivity of material versus temperature. And this is a specific example of gallium arsenide. And you can say there's a peak. This is in bulk material. This peak is typically between 10 to 20 Kelvin. And then after the peak, the thermal conductivity drops below the increases. And this actually reflects different physics. So at a very high temperature, okay, the each mode carry energy kT, right? So the number of photons is also proportional to T temperature. And in this case, what happens because as the temperature increases, you excite more photons, and they scatter each other. They scatter each other, and they drop the thermal conductivity. So that's why the thermal conductivity is dropping. And in fact, if you follow the argument I was saying, the number is proportional to T, the thermal conductivity is typically inversely proportional to temperature, Kelvin. But see, that's a simple picture, and then in reality, this exponent is not 1, it's typically dependent on material between 1 and 1.5. And people still are trying to figure out why it's not exactly 1. Okay? So this is a higher temperature range. And as you go to lower temperature, the photon scatter, the lattice wave interaction with itself, becomes weaker. So in this case, so the thermal conductivity will increase, right? Even though if you go to check specific heat of which in this dielectric is due to photons. Specific heat is typically this curve, okay? I forgot to show one, and it's not a constant. It increases from low temperature to high temperature. But thermal conductivity, so even though there's less energy, specifically the measure of photon energy, less energy in this region compared to this region, but because less scattering, the photon goes longer. So the thermal conductivity actually increases. Okay. So so in this region is typically photon scattering is no longer dominant. You've got the impurity atoms. So, for example, in silicon, if you have phosphor or boron, you dope it, right? They are lighter. So you think about it, you have a string. Again, photon is the lattice vibration. You have the same mass ball, and suddenly you put a different mass. That created some scattering of the waves. And so this is the region where the limit. The peak here is very much limited by these impurities in the material. And then, when you go to very low temperature, so the mean free path becomes very long. In fact, even you make a bulk material, the mean free path is longer than your sample size. So in this case, the boundary scattering becomes dominant. And the mean free path now is no longer dependent on the frequency, but is limited by the sample size. So in this region, the thermal conductivity is exactly due to the specific heat. So the behavior is just specific heat times sample size. So yes.
No question, because I just think it's because the specific all follow the T cooling power. That's why
That's exactly the reason, right?
Okay.
So by the way, this is why black body radiation is the fourth power, right? Specific heat is the third power. The energy is du gt. So if you integrate, the energy is the temperature fourth power. And the photon, this is the regime. Unfortunately, this is very low temperature regime. But this regime, photon behave almost identically to photon. No scatter, very weak scatter. So you can see the temperature power is the same. Okay, so that's a typical behavior of lattice thermal conductivity in crystals. And just give one example, the highest thermal conductivity material is diamond. And if you purify the diamond, you can change this peak by from this peak. Diamond at room temperature is about 2,000, and that peak will go very high. And if you purify, just to say even isotopes, right? Carbon 12 versus carbon 13 can significantly limit this the peak. Even at room temperature, the thermal conductivity will be influenced by the existing isotopes. Okay, so now if I combine the thermal conductivity, right, it turns out lattice has a contribution. The electron also carry heat. So if I have electron, I have hole. Hole also carries heat, right? So I have electron hole, and then I mentioned when they move, when electron hole or diffuse, at the higher temperature region, you may get more electron hole. When you go to lower temperature region, they have less electron hole. What happens? The electron and the hole will combine each with each other and give off heat. So in that case, they carry really potential energy from one place to other, and this is a bipolar contribution, which is really bad for thermoelectrics. So this is an example. Most people do thermoelectrics don't pay attention to it, and that's wrong. Okay. For example, the electronic contribution you can calculate it from Wiedemann-Franz law, right? The electric conductivity divided by thermal conductivity is proportional to temperature Lorentz constant. We mentioned Wiedemann-Franz law. So many people will do this. They will calculate this term and this term, and they measure this term, and they subtract the difference to give you the lattice. But they don't calculate this term. Okay? And this is actually difficult to calculate, let me see. And that's the reason. And but you can see that the thermal conductivity at a higher temperature goes up. Okay? The lattice thermal conductivity always goes down. And the reason for this goes up is due to this term, a very strong signature of bipolar thermal conductivity from electrons and holes. And correspondingly, the feedback goes down, right? The feedback because the electron hole cancel that heat, but the thermal conductivity is still getting both terms, incremental. Okay. So now let's go back. I've talked a long time on this figure of merit, these parameters, electrical, feedback, thermal conductivity, and we split the thermal conductivity into electronic part and photon part. And now if I divide this by the electric conductivity, so here I have Lorentz number, and here I have photon divided by so sigma t, right? That's just the say simple manipulation. And the Lorentz number in metal, that's the exact number. But when you go semiconductor, this depends on doping. So I have that's why I write the L as a function of n. But see, if you look at it, in metal, feedback cancel each other. The electron above the Fermi level, electron below the Fermi level cancel each other. You don't get a high feedback coefficient. So you plug in those numbers, the best you get in most metal is about 0.01. Okay. When I first wrote the thermoelectric proposal, I didn't know whether metal was good or bad, or semiconductor. So, well, now you take a good thermoelectric, right? Bismuth telluride, that's a typical example. And feedback is about 200 microwatt per Kelvin. And photon thermal conductivity is about 1. Electrical conductivity is 10 to the 5th Siemens per meter. So Siemens is just the inverse of ohm, right? So that's the unit of electrical conductivity. And then you plug in all those numbers, and then you find that's of the order of 1. So from 1950s to 1990s, the best thermoelectric material have a figure of merit about 1. People have because of the experimental you can get better. So people are reading a lot of papers on why we can't break. This is the absolute maximum. So they're questioning whether their theory trying to say why this is the maximum. Okay. So this is the theoretical foundation we've taught, and the last slide on this is material. I said sometimes you may get a really good one, but you throw away because the doping isn't right. You can say that because the doping determines where is the chemical potential, right? So the properties are so intertwined with each other. Seebeck coefficient as a function of doping, right? Here is bipolar effect. In fact, this one, why it goes down? I have to check. The electric conductivity, this looks bipolar. The electric conductivity increases, and thermal conductivity, and you peak your ZT at a certain value, right? So this is clearly, so you have to really twist your dopant. That's adding other materials or creating their different ways to create dopant carriers. So this is the difficulty with thermoelectric optimization. Not all work one has to do. Okay, now we're going to really just say what are the materials. Yes?
So that graph, was it actually measured experimentally?
This curves?
Yeah.
This curves were calculated.
So they're calculated.
Right. Yeah. But the typically when you say show dots, that's mostly experimental.
Okay.
Okay. Those are experimental. What do you see here is experimental. So this is a say summary, not always updated, and people always reporting progresses those days. So here is a summary of ZT of different materials. What people have traditionally been using, bismuth telluride, that's in all the modules, commercial module you buy. And this is as a function of temperature, right? So this commercial ZT kicks around room temperature. 1. And lead telluride is in the intermediate temperature, 400 degree, 500 degree range. And the peak is less than 1, 0.8, 0.9. And the silicon germanium, this is what NASA has been using. NASA uses for space missions. They use nuclear as a heat source, and but they build their system so the hot side operates at very high temperature. So silicon germanium is what NASA used in the past. And remember, if you want to build a device, you have to have both N-type and P-type materials. So it's not all shown whether it's P-type or N-type, but for each type you build a device, you need both N and P. And also, ideally, if we look, go back to look at the notes in the device section, when we talk about device, you want these two materials close, properties close. Otherwise, it's not the material that determines your efficiency. So you look at the same temperature range, what materials are available. And like I said, ZT has been one most of the time, and there are some recent progress. We'll discuss those progresses. Okay, this is a more traditional material. Like I said, bismuth telluride, lead telluride, silicon germanium, N-type, and P-type materials. And sclerotite is some newer material. So the commercial one is bismuth telluride, right? Bismuth telluride, go to periodic table. I can't remember all those positions every time I sit in my office and look at the periodic table. But those are heavy. That's so bismuth, tellurium are heavy elements. And why we want heavy elements in this case? Why it's good? So you look at it as it becomes heavier, the band gap decreases. Here, this is the band gap. The band gap decrease, it's typically about, you need for the band gap versus temperature range, around 10 kT, okay, 10 times kBT. kT. So at room temperature, the kT is 26 millielectron volts. So 10 is 0.26. Turns out the bismuth telluride band gap is about 0.15 range. So you go to say heavier material, your band gap decreases. And now you think about thermal conductivity. Recall that when I say the vibrational frequency, right? Vibrational frequency is spring constant divided mass square root. So heavier mass, you got the lower vibrational frequency. Lower vibrational frequency, you look at the group velocity, it travels slower. So the photon lattice waves go more slowly than the lighter atoms. So that's why the thermal conductivity is lower when you go to heavier materials. So bismuth telluride has a very complicated unit cell. This is really, in terms of full periodicity, when you consider a hexagonal unit cell, is really 30.7 angstrom. Many atoms here. And it's interesting. This is where when you really want to understand the material. So it's a tellurium, bismuth, tellurium, so layer structure, right? And this is the tellurium. This is the bismuth, tellurium, and in between the layers, you got you see here is a tellurium. This is a van der Waals bonded, and here is more mixture of covalent and ionic bonding. And there are a lot of studies, people look at which layer is conducting electron, which layer is conducting hole. And it's really, if you we're still working on bismuth telluride, and it's important to understand those details because people have been working this many years. You want to do something, you need to look at detail. Where are they? Which are the layers conduct electron? Can you think about something that you can, for example, still get the electron transport well in this layer, but screw up the photon, kill the photon propagation in the materials. So people calculate the band structure. I'm not going into detail. This is a really, unless you do this, this band structure calculation is also relative standard. You do density function theory calculation. And this is a pure bismuth telluride. If you just do pure bismuth telluride, the ZT, the best is about 0.6. Okay? And how you get 1 is really by alloying. Alloying, so you can further reduce thermal conductivity by alloying. So bismuth telluride is a compound semiconductor, and they look at the same column of the periodic table. One we are thinking alloy is same column periodic table. And then you substitute, for example, bismuth by antimony, and that way you could reduce thermal conductivity. And the best example of alloying reduced thermal conductivity is silicon germanium. Okay, and silicon germanium, this is not a thermal conductivity unit. This is the inverse thermal conductivity unit. So here is silicon, very conductive. The thermal conductivity of silicon is about 150 watt per meter per Kelvin. And germanium is also very conductive, about 60 watt per meter per Kelvin. Okay. Now you mix a little bit. You can say this is not a linear curve, right? You mix a little bit silicon with germanium, your thermal conductivity drops sharply. And the lowest thermal conductivity here, your inverse state is about 6-7 watt per meter Kelvin. So you drop from 100 to about 6-7 by alloy. And this is because, again, if you think about it, you have atomic chain, right? First, you can try with the pure atoms there. Second, you max up the atom periodicity. The wave becomes frustrated, and so the thermal conductivity will drop. So this is one way of scattering, and that's all thermoelectric materials that are made of alloys. And the typical thinking of the alloy is in terms of scattering, create additional scattering. And you can see here, this is a Rayleigh scattering relation. What is Rayleigh scattering? You go outside in a sunny day, you see blue skies. And the blue sky is the blue light gets scattered. And high frequency blue light compared to red, right? Solar radiation. The high frequency scatter more. So here is the Rayleigh scatter regime. That's a Rayleigh scatter, high frequency. And the sound wave is typical. That's people model it. High frequency is the inverse time. So scatter time, relaxation time is shorter. So that's a Rayleigh scatter. And then this depends on the mass contrast, and also depends on lattice parameter, lattice constant contrast. Those theories were done in the 50s. And in fact, I have a lot of suspicion whether they are truly valid or not. And but see, that's what the people do it. This is just the current status. Most of theory. And the problem is, you go to think about thermal conductivity. I showed K equals 1/3 CV gamma integration. And integration is very forgiving. Okay? In the sense, if you make an error one place, you make up the other place. And when you don't have exact theory there, and you got a lot of fitting parameter, and that integration can help you publish a paper. But the details very often are missing. Okay, like I said, this is typically that's how people make the material. Bismuth in P-type, bismuth, antimony, and this X is about 0.3 to 0.5. And then the N-type material, bismuth, antimony, and with selenium. And if any of you actually is from physics department, you probably went to, I remember a few weeks ago, there was a seminar on topological conductor. Turns out that this material now is very hot in the physics. People are looking at antimony telluride, and it's a topological conductor. So very hot topic there. But see, we don't know whether that has any implication on thermoelectrics or not. And doping, you can always add other materials as dopant, but see, here typically is by defects, the so-called anti-side. So if you look at it, it's possible that bismuth go to tellurium side. And this is particularly because bismuth and tellurium, their so-called charge, electronegativity is very similar. So they can, when they exchange positions, the disturbance crystal is small, but the number of charge is different, so that creates either holes or electrons. Okay, so now we're moving to, so that's traditional material. We're now moving to more current materials people are talking. This is a oxide. It's sodium cobalt oxide, and this were originally started in Japan. Terasaki made a lot of contribution to this, and it turns out people are interested in oxide since 1980s. Why? That's because the high temperature superconductor was discovered out of oxide. It's surprising. YgCO, yttrium, boron, copper, oxygen, and that got lower price, right? See, so the transitional temperature now in this high temperature superconductor has reached probably around 130 Kelvin, 140 Kelvin. But see, superconductor itself is not interesting for thermoelectrics. Why? This is because there's only one quantum state. So the entropy is zero, log of quantum state, right? That's the Boltzmann relation. Entropy carried by, is a log state. So superconductor is not interesting, but this one is not a superconductor, and people have achieved about Z equals 1 at, I think this is around 800 degrees Celsius. So it's a high temperature application. half-Heusler. I mentioned this material because if you go to Japan, I talk a lot to Japan thermoelectric guys and also from company. Whenever you work on, you look at the bismuth telluride, they are aware. Japan is very sensitive to this because they have limited amount of materials, right? It's a small country and the resources are very limited. So they don't want, they always say, can you make out of this abundant material? What are the abundant materials? Silicon and aluminum. So those type of materials. And so this is one example where the material is quite abundant: nickel, tin, and titanium, and it has reached a reasonable figure of merit. And this is where, for example, you look at even with this figure of merit, thermal conductivity is still very high. Why is it still very high? Why I say it's very high? Because you always think of bismuth telluride. That's a good number to remember. Thermal conductivity is about 1 or 1.5. Seebeck is 200 microwatts per Kelvin and electrical temperature. So if you look at this, the thermal conductivity is in the denominator. And you get this good ZT, that means the electron is really good. Right? S squared sigma, that's the power vector, is pretty good. Can you kill this guy? Can you kill it? Thermal conductivity, reduce it. Particularly, can you reduce the photon part? You don't just want to reduce because the electronic also make part of the thermal conductivity as part of thermal conductivity. Okay, so people now are looking into, if you look at the past materials, right? It's typically bismuth telluride, lead telluride, silicon germanium. Those are simple structures, simple compounds, two element, binary, right? And now people are going more into more complex structures. And why complex structure? Yeah, from thermal conductivity point of view, there is a good reason there. This is a few lecture back. I was talking about the modes, right? In terms of optical photon, acoustic photon. Optical photon is very flat, and acoustic photon is really the one that carries heat. So when you got a lot of atoms in the unit cell, you have a lot of optical branches. So those optical branches don't carry much heat. So the more complex is the crystal, typically the lower is their thermal conductivity. And that's only a very simple hand-waving way of saying it. And of course, you can say some of this material has really low thermal conductivity. Bismuth telluride is here, right? And this, particularly, I want to point out this zinc antimony. Zinc is abundant. If you can make zinc is a good one if you can make the work, right? And it has very low thermal conductivity. And in fact, zinc antimony thermoelectric figure of merit now has reached, I think it's about 1.4, pretty good. Except that there are also issues, material stability. And when you heat up to high temperature, zinc speed up. I have seen pictures showing that under temperature gradient, the material grew hairs. Okay, here are zinc coming out. So you got a lot of material reliability issues also. And but generally there are now people looking into a lot more complex structures, crystal structures, and a much broader range of thermoelectric materials. I mentioned this already, but now let's look at the ideas, right? We said complex structure, and this is another idea that's really interesting because alloy, if you think about silicon germanium alloy, and it's really germanium go to silicon atomic site. So you can think that as a substitution, right? So germanium substitute silicon atom. the lattice, if you think about cube, right? And let's take a crystal structure. Think about cube, and the silicon sits in the corner of the cube. And now you take out the one of the corner, you put the germanium. And so this is a substitutional type of, I call that, you can think of the impurities. And sclerotides is a simple, interesting material. This is a sclerotides is cobalt antimonide or iridium triantimonide, iron triantimonide, that type of structure. And what's interesting is that it has a very large unit cell, a lot of atoms there. And also in those unit cells, so here we got two vacant. So you can say this each is a square, right? But in this 8, how many? We have 8 cubes. 6 of the square has atoms inside. 2 of them don't have anything inside. So there is an open space there. The open space gives you opportunity. Let's put another atom there. Put another atom. This atom has a very different characteristic from the host atom, cobalt antimonide. So the idea is like a ratter slate. You put an atom, rattle around, and this rattling will disturb the normally periodic lattice waves in the surrounding material, surrounding the lattice itself. So that was called full-on rattlers. And the next one is an example of, you can say cobalt antimonide, and you fill this with other rattler, lanthanum, and people try it many different ways. This is still, I said, I was in a meeting last week, and people are still putting, first with one rattler, one atom, one type of atom. Now people got to 3 rattlers. Well, the hope is each rattler have its own rattling frequency, and you kill the whole acoustic frequency of the whole lattice waves. So this is clearly a very dramatic decrease in the lattice thermal conductivity. And people have done neutron scattering to actually look at the atomic displacement in these materials. So you can see here, this is a lanthanum, cobalt antimonide, right? So here you have iron, cobalt, that's their atomic displacement. So inside is doing Brownian motion, and this measurement can actually measure what's the amplitude. This is the Armstrong square, you can see here. And what's the amplitude of that motion. And the lanthanum they put into the cage there seems to be have a very large amplitude here, you can see. And the theory is that this scatter the photons. I think the theory is still evolving, okay? And the explanation, people have came up with different explanations. But you try to do the modeling experiment to really make this good material. Here is the, this is a, I think, I forgot whether this is P-type and N-type, but I do want to tell you a story. Many years ago, people reported P-type sclerotides, cobalt antimonide, have a figure of merit equal 1.4. Okay? And now, nobody can get 1.4. Everybody, the best they can get is 0.95. And the reason, this will bring up a very important point, thermoelectric research, measuring this property is tricky. Okay? And you have 3 properties to measure: electric conductivity, thermal conductivity, seeback. And even if you are very good, each property you say, okay, I have about 5% uncertainty, which I think is pretty good already. And you go to calculate your uncertainty range, and that's about 15%, right? And it turns out that many times your system can take the same sample So you do thermal conductivity, take a sample. You go to pick another sample for electric conductivity, and you measure wrong things. And sometimes if you look at the bismuth telluride, it's layer structure, right? The property is very anisotropic. This will be really dangerous. You measure even the same sample. You measure property thermal conductivity in one direction, you measure electrical in the other direction, and you can just get a good ZT. That's not true. So this is every time you go to a meeting, people will be debating. And most of the time, people are skeptical of any report. Okay? It's just difficult. Because measurements are difficult. Okay, now I turn to my favorite, right? Nanostructure. I said that they're bulk material. People look at different material, different crystal structures, Folon Rattler. Those are all working on crystalline materials. And there was, say, this nanostructure approach was really Millie Dresselhaus in the EE department at the time. And the story is, this is a really a good story, okay? In around the 1990, U.S. Navy started to rethink thermoelectrics. So they went around and they came to Millie whether she had any idea on thermoelectrics. Millie didn't work on thermoelectrics before, and but she thought about it, and there was a physics student walking into her office wanted to ask her whether she had a topic. So she said, "Oh, why don't you look at quantum well, whether it can give better thermoelectric properties?" So the student looked at and did it's really a homework problem. I'll show you later. And but the calculation turns out to be really interesting, and a lot of people start working on that. So sometimes a simple idea really stimulates research. And here, this is a slide that I tried to make, and seeing the potential of using nano. So you think about the electron and photon. Electron is what carries heat around. And of course, they are quantum mechanical, they are all waves. We mentioned those waves before. But they have different wavelengths. Okay? And it turns out it's a spread. Okay? In real material, it's always a spread. And we need to look into details. But in general, actually, electron wavelengths can be longer, average speaking, than the photon, heat-carrying photons. And so that's sort of order of magnitude that I often use. But again, each material is different, each temperature is different. And the other is the mean free path. Okay, that's the average distance electron-photon travels. So you look at one possibility is really look at the wavelength difference. And because the wavelength difference means an intuitive picture is that if you have a surface, whether it's smooth or rough, right, really depends on the feature on the surface versus the feature of the wavelength. Right? If you have visible light coming towards a surface like this, it looks rough. It scatters light to all directions. But if you have really a microwave coming in, very long wavelength, the surface will be smooth. Much, a wavelength larger than the roughness features. So one of this idea was, if you recall the thermal conductivity, right, the curve. At a very low temperature, the thermal conductivity increases with the specific heat, because the mean free path equals sample size, is limited by sample size. So low temperature already have the size effect. And if I make this structure very small, that size effect can shift to high temperature. As long as so small enough so that they like take a wire or film. If the diameter or thickness is comparable to mean free path, now the photon will no longer is a photon-photon collision. They will collide with surface, right? And another simple intuitive picture is, okay, what happens here at the interface of two material, right? You have the lattice wave coming in, and at the interface you hear echoes. Well, we hear echoes for the visible range, audible range, but say in the heat carrying is terahertz, right? Depends on. So those are high frequency. You still got the same phenomenon happen. And then echo means some heat don't go forward anymore. So you could use those phenomena to draw the thermal conductivity. And Miller's idea at the time was squeeze electrons. Okay, so quantum effect, which I'll talk more. But now think about the quantum effect. Electron is a ball. Wave function is a function. The s orbital wave function is a ball. Okay, and let's say this is the size of the ball. Let's say 100 angstrom, right? Now you feed this electron. You make a film only 10 angstrom or 50 angstrom. What happens? The ball is no longer a ball, right? Once when I was a student visiting LBL, there was an interesting analogy made by Professor Chen and said, think of this. You put a basketball into a pizza box. You squeeze that ball, you have energy quantization. So so you have this wave, and then when your size is small, you quantize the wave. And ideally what you want is this wave is under ideal quantization, you want a smooth surface. Okay, you don't want the interface scatter electrons. And it's possible, again, you think about the wavelength range, right? Because whether a surface is smooth or rough depends on wavelength. For the case of electron, the scatter is the electrical potential. Your potential, whether it's rough or not. And for the case of photon lattice wave, fundamentally it's all electrostatic, but it's really you can think of mass spring, whether the force is rough or not. Okay, and so you actually have the potential. If you think about the photon and the electron, your electron, if you quantize it, is smooth. And because of the wavelength difference, you can potentially actually have the same surface be rough, right? For photon, the acoustic wave. So this will be ideal. Your dream. You want to screw up the atomic vibration, but electron can go as a waveguide. That would be one scenario. And people started a lot since many, and in fact, I should say, at the same time, maybe go to other places, and the people have a similar idea, although Miller did a really a good calculation. This superlattice idea was from Rama, from Harmonium, and what he did is the perpendicular direction to superlattice. And this is, you can say, the experiment. Thermal conductivity had dropped, right? So the business telluride bulk is about 1.2, and they dropped to 0.5. Very difficult measurement. And this is where I start getting into thermoelectrics. So my thesis, when I did my PhD, I was looking at the superlattice heat conduction. I was worried about lasers, not thermoelectric. I didn't know anything about thermoelectric. And but the electron here decreased a little bit. This is S squared sigma. The power factor, S squared sigma, decreased a little bit. And in the case of, this is a Tehama and Nikon lab, he grew this lead telluride on lead selenide on lead telluride, and because the lattice constant is very different, the strain. So you grew certain thickness, the strain will break up the film and form dots. So he grew those multi-layer structures, and this picture, I don't think this is from him, I don't remember. But what he showed was, again, no thermal conductivity and the power factor about the same. So at the end, it turns out that historically, it's the thermoconductivity alloy, institutional, right? And now with this nanostructure, it turns out that really thermoconductivity seems to be a very effective strategy. But let me again caution. Almost now, see, everybody questions those results. Okay? It's a very interesting result, very intriguing, but it's a very hard measurement. And Hamann retired. He's very respected, and I talked to him a lot. He has a book. If you want to understand thermoelectrics, he has a very good book. Not many people read because it's too difficult. But it's very good if you read. And the first picture, I remember the first 2 pages was talking about electrostatic potential. As a mechanical engineer, that's always been hard. Understand what's the electrical potential, what's the chemical potential. Okay, and Rama Winkler Thermonium is from RTI. They have a spin-off company trying to do those superlattices for microelectronics cooling. And if you're interested, you can check Electric. That's the startup's link. And the superlattice, I guess the challenge is grew very thick and also reduce the cost. So this is where my story is. I said I have been working on this for a long time. Since my gallium arsenide was really used for lasers. And so those are experiments. Along the film direction, you can see it's anisotropic. This is silicon germanium of gallium arsenide. Let's say the superlattice structure, right? So this is perpendicular to the film plane direction, parallel to film plane direction. And the problem is, if you think about this superlattice by its name, superlattice was invented by Ritu and Isaki. Isaki got the Nobel Prize for his work in resonant diode. Okay, that's before he invented superlattice concept. And the name of superlattice means you have a supercrystal. And so you see, let's say this is one layer, this is another layer. Now you look at a unicell is no longer cube, but tetrahedral that cover from here to here. One period of a crystal, right? So that's what the name implies. If you have this, according to the name, this new crystal, you can calculate the new energy photon spectrum. You calculate group velocity, you calculate density of states, do all this calculation. And then you do 1/3 CV gamma. I don't know gamma. So, but I know I can, from that calculation, I know C and I know V from density of states and dispersion. And that's the curve you get as a function of thickness. It's not correct. Okay? So basically, the picture is not about forming a coherent structure. People are still debating, so I don't want to prejudice you. You should read literature. And that's my own prejudice because I've been doing research on that. But when you get into it, say, oh, I don't believe that. Look into literature. Look at the different sides of the argument. Okay? And so when I go to look into the other picture, just say, okay, now I got the surface. I only just consider not this supercell, just 2 layers, and of course periodic structure, we consider all that. And then we got the interface roughness. And that roughness scatter photon diffusely, and that can cause the thermoconductivity reduction. And here I got a fudging parameter. Yes?
When you say roughness, are you talking about just like obstacle spacing, like an electron diffraction or any other diffraction experiment? Or like you expect something to be scattered by something with a spacing near its wavelength?
Right. So that's a very good question. And what's the mechanism of that roughness? And it turns out that, let's say, when you brew superlattice, molecular beam epitaxy, and then you find out that there in the 80s, there are a lot of studies. Gallium arsenide is the best studied system. And there are diffusion of atoms between the layers, about 1 to 3 monoatomic layers. And I said the photon wavelength is very short, right? So my picture is really the atom. If it's a perfect periodic, you say the atomic space is all periodic, the same atom, then you should not have that. But now if you just have one atom protrude, and then random distance later another atom protrude, and that's, say, a surface, whether it's rough or smooth, is about 1/10 of the wavelength. So if you go to optics, so here again, we don't know exactly. So you go to optics, when people say whether surface is smooth or not, it's about 1/10 wavelength, right? 1/10 wavelength, you look at the phase of the wave. So here, because the wavelength of photon is about 1 nanometer to 10 nanometer range. So a little bit of atomic diffusion can cause that. But there are a lot of puzzles at this stage, okay? You should read David Kihill's paper from UIUC. And they have done constant diselenide and some newer mature system, and they found that they can have thermal conductivity really, really low. The lowest they have is twice air, solid, fully solid. Anyway, so I say this is the picture I have, but I think there are probably more things that we need to develop. Okay, so but see, from this picture, what I conclude is, okay, we don't need a periodic structure because if it's not a unicell type of picture, then I don't need a periodicity. So that's what need us to do this random composite structures, because that way I can do lower cost. And so we try this and it works in some materials, right? This is a latinoite. This is the nano. This is the bulk latinoite, and this is nano. Bismuth telluride. Bismuth telluride, bulk and nano. And it turned out, say, what we do is just ball mill material and recompact them into nano form. It worked in bismuth telluride, worked on silicon germanium also. Didn't quite work in that telluride. That telluride is green group. And sclerotite didn't work out either, and because of green group. So we're still trying to figure out how we can stop that growth of the grain, and we drop the thermal conductivity. Yes?
What about the quasi-crystals?
Yeah. That's a very good suggestion. And I didn't look at quasi-crystal, but there are people looking into class rate.
What is
Class rate is very complicated. Like you can have silicon in the class rate, germanium in class rate. It has it has holes inside, and they have low thermal conductivity. But for that crystal, the K class rate. The K is whether you can make the electron still move. Remember, you can kill photon. If you just want to kill photon, that's easy. But you also want to keep the electron moving. So the idea, very good terminology came from Glenn Slack. And he said, what you want is electron crystal, photon glass in one material. Because the photon in glass, this glass here, amorphous random atomic arrangement. So the photon thermal conductivity is very poor. But this superlattice is different. Right? It's still crystal. So you are, whether we can, for example, we're looking into whether we can randomize the wave, localize even localize the wave. Very difficult, I think, but it's worth trying, right? And because so you need a crystal structure to get an electron propagating. Very difficult because the short wavelengths. You can do photonic crystal or that for electromagnetic wave because the wavelength is pretty long. But it's very hard to do this for photon because wavelength is short and they don't propagate very long. You need a long coherence to have the waves distract each other. So those are the difficulties. Okay, so here are more detailed example. This you can see the thermal conductivity drop. So when I started this, everybody was saying, electron, what are you going to do with the electron? I said, I don't know. I wish it worked out. But when I think back, you actually have good reason. The general idea is, okay, let's don't get too much electrical potential offset at the interface, right? That's what the scatter electron. And but say it turns out in bismuth telluride, you can say the electron is better. When I first looked at this, I couldn't believe it, right? And the reason is, of course, it's semiconductor. The electric conductivity depends on the carrier concentration, right? It's the mobility times the N, the carrier concentration times charge. So it turns out the bismuth telluride, when you ball mill it, you generate defects that generate the more electron, or in this case, the more holes, because it's a positive. You see Seebeck is positive, that's holes. Again, you can say that's the typical behavior. So at the end, if I plot the S square here, so higher electron density, lower Seebeck, right? Higher electron density, Fermi level is closer to the band edge, or even getting to the band. The Seebeck is the average distance thermal energy of electron relative to chemical potential, Fermi level. So higher electric conductivity, lower Seebeck, that's all normal. But because they have higher carrier concentration, the bipolar decrease starts later. You can see here, right? Go to higher temperature. And then, so if you plot S squared sigma, this is actually better than this. We tried that very hard in superlattice. We didn't get the S squared sigma. Both decrease thermal conductivity and increase power factor, and this actually worked. So, but we still don't know how exactly to model it. Very difficult to model in random structure. We're doing not. And we're not the only one. Let me say, in fact, Mercury Colonizadis has been working in this material system, which we call LAST. And so were that antimony telluride, and it's single crystal. He grew single crystal. It spent several days to grow single crystals, cooling, heating, and got the very good properties. And again, let me caution you, I can't believe this point because he extrapolated. Now he doesn't show this anymore. And measurement is always a hard problem. This is one has to realize. Sometimes I steer people away by saying that, but that's reality you have to face. And what they found then later on is that in this material, actually, even though it's a single crystal, but a lot of precipitates are from nanodots. And with that, his thermal conductivity is also quite low, so we got a good figure of merit. This is a really interesting system. I've been talking to Jules Karamas, Dan Morelli, and I still can't really give you a very simple picture. And it's basically, I've asked Jules, give me a very simple picture so I can explain to my students. And I don't think that I got his simple picture yet. But the idea he's looking at is here is a silver bismuth selenide, diselenide. It's a cubic structure, right? Silver antimony telluride, all those are similar. And what he's saying is the electron clouds between the atoms have overlap, and when one set of atoms is moving, that squeeze this clouds very significantly. So electron clouds very significant squeezing cause the force anharmonicity. And this anharmonicity gives a very low, so what you want is you want to make the atoms strongly scatter each other. Okay? High thermal conductivity, if you just have a pure spring harmonic oscillator, you have infinite thermal conductivity. And the finite thermal conductivity really comes from the third term of the potential. Okay, it's not a F equals kx. It's for F equals kx plus perturbation kx squared. So that square makes the two different frequency waves interact with each other. That's so hard for optical wave. It's much easier for phonon. But when you want to push to very low, very small limit, you got to say get this harmonicity very large. And one way to gauge that is this recent parameter, which is related to thermal expansion. And thermal expansion, so higher large thermal expansion material typically is more unharmonic. Okay, and what is showing is this minimum thermal conductivity theory. That's also another thing I never believe. Minimum thermal conductivity. What the idea is 1/3 K equals 1/3 CV gamma, right? That's the kinetic theory. And the minimum thermal conductivity is replacing the mean free path by the wavelengths. Okay, so that's the minimum mean free path you could have. And this was a Glenn Slack original theory, and then David Kihel and Bobby Paul from Cornell said that, oh, you should not be just mean free path equals wavelengths, it should be mean free path equals half wavelengths. Einstein, based on Einstein's argument. So that reduced thermal conductivity minimum by another half. And so very often people will draw this thermal conductivity against the minimum. So this is one example. I say, okay, you reached the minimum. You can't reduce anymore. But in fact, I said David Kihel because he measured layer structure. His thermal conductivity is twice air. It's orders of magnitude smaller than the minimum. So his own minimum theory, no, there's a minimum, it's an experiment that's an orders of magnitude smaller. So that's why I say I don't believe in the, because you should go look at their better formulation when you have an anisotropy. You don't have 1/3 CV mean free path. Okay, if you're interested in this, I'll point you more to literature. Okay, this is something that I really don't want. I said I bring you from the basics to really the forefront. That's just a few months ago. There was a paper on indium satellite, and what is saying? This is a charge density wave, and the Pierce instability, and this got really. But let me try. So what happens is this direction is one Pierce force. That's more like a layer structure. And then into the C axis, that's the covalent bonding. But because the charge distortion, so in the C axis, this actually charge is strongly distorted and create a very large unharmonicity to the lattice wave scatter. So the thermal conductivity is really strange because the van der Waals direction force, weak force, typically means low thermal conductivity, right? But in this case, what you have, this is the CX covalent direction. It has lower thermal conductivity than the van der Waals direction. And very interesting, and definitely worth more study here. Okay. Now let me go to milliside here, right? This is the quantization I mentioned, and the pizza box problem, right? The box going to pizza box. So you have a simple, this is a simple homework I said before. This is the z direction, energy is quantized, and you can do the same standing wave argument I did before and see what's the wavelength and what's the corresponding energy. And so x, y direction, it's quasi-continuous wave vector. So now for different n, we have the subbands. So this energy quantized different energy levels in the due to the thickness in the z direction. So that's a basic quantum well idea. Okay? And now you go to do this. You calculate the density of states. I don't want to go through this math, but you can say this is the same thing we did before, except in z direction. Now I do not convert the summation into integration in the z direction. I convert the xy direction. Because z direction, that separation is too large, and the summation into integration, that conversion is not rigorous, not mathematically accurate. So I still keep this summation here. And at the end, what you show is the density of states now is a staircase. Or in typical parabolic band approximation, we got this is 3D, this is 2D. Okay? And now, with that, there's an advantage. Where is the advantage? Let's go back to the picture I showed before. Right? Seebeck is a measure of the average energy of the electron relative to capital potential. The electric conductivity is really proportional to the number of electrons. Right? Now, when I have this, if you look at it, this is density of states, this is GF Fermi-Dirac derivative. Now, this is very small. It's this times this. That's the region where it's contributing to electrons. Right? Because of the parabolic, this is a small number times small number. So the electric conduction, the number of charges that carry this Seebeck, most of them is a very low energy. The average energy is here. Those are low energy electrons. They carry more electric charge. So that's a problem with the parabolic band, with the density, the parabolic density of states. Okay, now you do the quantum one, right? You have a sharp staircase, and you can put in, you see here, you can put in more charge, or still have the same Seebeck. Or if you have semi-electric conductivity, then you can increase the Seebeck. At the end, what you want is S squared sigma to be larger, right? So that's why those quantum structures, like the quantum wells, can give you larger S squared sigma. And then you look at the other quantum structures. The density of states, this is the staircase for the two-dimensional, and then wires is a sharp peak here, and dots are just discrete lines. So progressively going from 3D to 2D, 1D, 0D is better. Progressively is better. Okay? So that's what the theory says. And at the time, Millie and Ted Hammond in Lincoln Lab did the experiment. And they showed that this, but I want first to show the trend is all right, except there's one caveat. You see there? This is not S squared sigma, this is S squared N, right? Electric conductivity is the N times mobility times the carrier charge, electron charge. Okay, and what's the reason is that the superconductor was not, the quantum well was not very good. Interface scatter electrons. The electric conductivity, if you plot that I don't know the detail, but let's say there are still questions here, right? Because this is S squared sigma, S squared N, not S squared sigma. But the trend is there, and that generates a lot of interest. And this is just a more calculation I took from a book that Joe Paramas and myself really are writing. We never have finished it. I do not want to finish this. But anyone wants to read, there is a draft. 3D, 2D, 1D. Okay. Progressively is better. That's a theory. And to do it in the experiment, like I said, you can't scatter electrons. You have to be very careful, right? So, and there's another problem. Okay, so of course, superlattice quantum well is just the film that's conducting electron. And the problem is you have to sandwich this, right? Or you can use air or vacuum or quantum wire in vacuum, then there's no leakage. But see, normally when you use another material to create a barrier to confine electron in the field, then you got phonons in this barrier. The phonons in this barrier will kill your conduction, right? So kill your, create a more heat leakage there. And there are solutions on this. Theoretically, I worked with Millie on this before. Let's see, it's just the caveat that one has to pay attention. For example, there are also studied by Jeremy and others say if you reduce the thickness, okay, you want to reduce barrier heat leakage, you reduce thickness. And then the different, then you have another quantum well, these two quantum wells start talking to each other, colony, and that colony actually is not good. That can, the density of states becomes less sharper than the pure quantum well case. There are potential solutions. I encourage you to read the literature, Millie, and then we work on this. But it turns out, this general idea of sharp featuring density of states is universal, not only in thin films, but in bulk materials. And there was one paper by Jerry Mahan, and he wrote a paper around 97, and he's a very good theoretician. He just took a simple math problem. He said, I'm going to optimize the density of states, just write the expression I wrote before, treat it as a functional. That D, density of states, as a functional, mathematics. What's the functional that will give you maximum S squared sigma, or give you maximum ZT? And at the end, he concluded this delta function. Okay? So delta function is the best. And if you go back to what I show here, quantum dot is best. Except the electron, how you go and move quantum dots, the electron going to establish delta T over quantum dots, right? So wire is also good. So this is a general principle. Another interesting comment I want to make is you go to check the Lorentz number, and that's what I suspected. The Lorentz number in quantum dot can be 0. Very strange. Nobody demonstrated it, okay? It will be an interesting experiment. Electric conductivity is not 0, but the electronic thermal conductivity is 0. It's very easy to check. Okay. Let me go here. So this is really recent experiments, and he said, we talk a lot, but a very smart guy, and he say, he worked on nanowires, bismuth nanowire, worked with Million. But I say, I'm going to turn to bulk material. So one day, he read Russian literature, and this all actually in Russian literature, and it turns out there's some doping. Typically, when we think about doping, we think about doping, the energy level is inside the band, in the band gap. But there are some other atoms, you dope it, the dopant level is within the conductional valence band. And in this case, is in the valence band, and this valence band, the dopant form additional energy states that create a sharp feature in the density of states. And this sharp feature led to very good C5 coefficient and a very high ZT, figure of merit. Very nice idea. The question is whether you can replicate it in different materials. Because with thallium, nobody wants to touch it. Okay, so it's very poison. Because say it's not that terrible. I have a friend that he said I worked with thallium for more than 15 years, superconductor, and nothing happened. But But of course, be careful. Now, this is another idea. I think again, come back to you can interpret the same as density of state. This is okay. Sigma coefficient. If your chemical potential is here in the band, this is negative, this is positive, so they cancel each other, right? Of course, this is larger, so you still have the cancellation small. But if you put a potential, so you have a particle or you have an interface that just happen to have this potential high, then those electrons are scattered. So that's called the energy filter or thermoelectric emission. I'll talk about thermoelectric emission in the next lecture when we talk about thermoelectric engines. That's a different way. But this is doing in solid. So you scatter this low energy electron, and then you only have high energy electron flow. And if I draw the density of state picture, is although there are electrons in this region, but I scatter them, they do not move. So now in terms of density state, what's really movement is they still have a per-product sharp picture. So that's my interpretation to this picture. Those different ideas. And you can always think about the density state sharp features for electron particles. But really, the one that has won so far, the only successful example I know is this one. Okay, truly work in materials. So most other approach that's successful is in phonon. So with that, I brought you from the things very simple to things I don't know. And you should figure out. Okay?